This is the video that I mentioned during my previous during my previous lecture. I mentioned this, that is, again, it's the path of the Orion spaceship, but in this case, they are also tracking the vector field, what force of gravity is acting on the spaceship at any given time. So that vector in blue is the gravity force from Earth, and then you don't see it until you get close to the moon, how the other one, the gravity force of the moon, affects the spaceship right in the nick of time, so the spaceship doesn't escape the pull of Earth and goes on forever into space. I think it's fascinating. And it is, again, just a representation, a visual representation of vector fields, which is what we're doing today. Let me continue with vector fields and integrals of vector fields. We're going to be talking about the fundamental theorem of line integrals. And you have already seen a fundamental theorem of calculus, which is the fundamental theorem of calculus. So the fundamental theorem of calculus, remember that it has traditionally broken in two parts. And one of the parts says the following, that if f is continuous and you know an antiderivative, then the integral from a to b of f of x is just the difference of the values of the antiderivative. So the whole integration, this we use all the time when we integrate, and it simplifies integration enormously if you're able to find an antiderivative. So that means that if you put everything in terms of f, of the capital F, of the antiderivative, that the integral of a derivative is just a difference of values of the function itself. So it turns out there is something like this for line integrals. So if you have a smooth curve and you have you're parameterizing by r of t, and you have a differential function, 2 or 3 variables, such that the gradient is continuous on that curve, then it turns out that the derivative or the integral, the line integral of that vector field, which is the gradient field, is equal to the difference of the values of the function f at the endpoints of your path. So we don't have to do any integration. We just have to take a difference of two values. So this is huge because some of those integrals can be very nasty. But if you know that that your vector field is actually a gradient, remember we call those the vector fields that are the gradient of a function. Those are conservative vector fields. So if it's a conservative vector field, then we can do better. So let me try to just go quickly over the proof just to show you what's happening. And it's just an application of the fundamental theorem of calculus. So remember what this meant? The line integral of a vector field along that path, it was the integral, if the path is parameterized by r of t, it was the integral of the gradient evaluated at the path times the derivative vector, and that times is the dot product of the two dt. But what is this? This is the derivative. So this vector, remember, what is the gradient is the derivative, the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, evaluated at rt, and then what is this? R prime of t. R prime of t is dx dt, dy dt, dz dt, where x, y, and z are the functions that are the x, y, and z coordinate of r of t. But if you do the dot product of this and this, what do you get? Delta f delta x times dx dt, this plus this plus this. Okay? And now if I just look at this piece here, and I integrate with respect to t, this integrated with respect to t, using the chain rule, is just f. So I can integrate that using the chain rule and using u substitution. I can integrate that as f of r t, and with the bounds between a and b. This is the derivative with respect to y. So those are going to be all the coordinates of the derivative, and then when you apply it like this is the derivative of this function. Now I can use the usual fundamental theorem of calculus to show that this will be f of rb minus f of ra. So let's try it out. Let's take it out for a spin and see what happens. So suppose I want to evaluate this. Let me first try to figure out what would this be if I didn't know the fundamental theorem. If I don't know the fundamental theorem, then I have to integrate the gradient field. The derivatives of f are going to be the derivative with respect to x, which is 2x e to the y, comma, and then the derivative with respect to y, which is x squared e to the y, right? And then I'm going to have to do the dot product with r prime t. R prime t is 3t squared. Okay? Do the dot product of the two, and that is 4x e to the y plus that's not how it works exactly, because I want to evaluate it at the path. Wait a second. So before I evaluate like that, I have to evaluate this at r of t, right? So now 2x is 2t, so this is 4t e to the y, which is t cubed, comma, and then 4t squared e to the t cubed. So when now you do the dot product, you're going to get something like 8t e to the t cubed plus 7t to the t squared, no t squared, t to the 4 e to the t cubed. And now I would have to integrate that thing between 1 and 2, integrate 8t e to the t cubed plus 7t to the 4 e to the t cubed dt. Are you with me? Any questions about how I set up this integral? And who has time for that? I don't want to do that when I can do the fundamental theorem. So the fundamental theorem tells me that the integral over that curve of derivative of gradient dr will be just f of r2 minus f of r1, because we are integrating a gradient. So I just have to evaluate f at r2 and r1. So let me first compute what is r2 and r1. We start at the point 2, 1, and we end at the point 4, 8. Right? F evaluated at 2, 1, if you plug in, that is 2 squared times e to the 1, so that is 4e. And f evaluated at 4, 8 that is 4 squared e to the 8, which is 16 e to the 8. So the solution is just 16 e to the 8 minus 4e. Well, that's it. Yes, exactly. So this only works for a vector field that is a gradient, or what we call a conservative vector field. But I gave you an integral that was a gradient, but now I'm going to tell you, okay, can you integrate this one? And you can do it the long way, in that I can parameterize this segment and do the whole integral like I just showed. Or we can try to figure out if f is conservative. If f is conservative, then I can skip everything, essentially, if f is conservative and it has the properties of the fundamental theorem, continuity and differentiability and so on, which the path is a straight line, the function is perfectly continuous, the vector field is all continuous functions. So can I find the question is, can I find a function such that this vector field is the gradient of that function? So the question here is f equal to a gradient for some f. So how do we decide that? If this was a gradient, so if the gradient of f is, I know what the gradient is, the derivative with respect to x, the derivative with respect to y, the derivative with respect to z. If that is yz, xz, xy, then what was f? xyz. It's not always going to be this easy, but we're gonna work on this in a moment to try to figure out how to do this in general. But for the time being, we have a good guess that f could be x, y, z. And if I look at the derivatives, the derivative with respect to x is yz, the derivative with respect to y, it's xz, and the derivative with respect to z, it's xy. So it matches. So that is what we call a potential function. Okay? So this is the potential for that vector field, is the function whose gradient is the vector field. So this is called a potential. So it is a conservative vector field. So now I can rewrite this integral, the integral of f dr is the integral of this gradient dr. And I know how to do that. That will be f of the beginning, f of rb minus f of ra. Okay, but I know where those where it's starting and ending. So let me do that here. This is equal to the integral of the gradient dr, and it has to be f of endpoint minus f of start point. We have figured out that f is xyz. So what is f of the endpoint? 4, 6, 3. That's 4 times 6 times 3, which is something like 72. And f of the start point, that's 1 times 0 times minus 2. That I can do in my head. That's 0. So this is 72 minus 0, so it's equal to 72. That's it. I don't even have to parameterize that segment. I don't have to plug in into F the coordinates of the segment. Boom. So the key here is that I'm using the fundamental theorem of line integrals. That is the statement of the fundamental theorem. So the fundamental theorem tells me that if the vector field is a gradient, then the values are just, the value of that integral is just the difference of the evaluating the function at the endpoints. If the vector field is a gradient. So in the first example, the vector field was already a gradient. In the second example, they give me a vector field. And what I'm saying is that if you figure out that this is a gradient, then we can actually figure out, then we can use the theorem of line integrals to just solve it very easily. Not every vector field is a gradient. Not every vector field is conservative, but many of them are. Yeah? Okay. So just as a reminder, then we say that a vector field is called a conservative vector field if it is the gradient of some scalar function. So if there is a little f such that the vector field is the gradient of f, and in that case f is called a potential function. So here we have a couple of examples. We've just determined that f is conservative, the first one, because if you take f to be x, y, z, then the gradient is precisely the field, the vector field they're giving me. So now, is G conservative? So how do we figure out if a function of our vector field is conservative? If so, the derivative of f with respect to x has to be the first component. Okay. And then what I can do is, well, what I know is that if I integrate this with respect to x, just an indefinite integral, that would be at least the sort of like the x, anything that has an x would be that function. Okay? So to try to figure out what is f, what I do is do an indefinite integral of x y squared plus 3x. And what that's going to get me is, well, I'm going to get a half x squared y squared plus 3 halves of x squared plus a constant. Remember that constant of integration? Here the constant of integration, because f is a function of x and y, and we are integrating with respect to x, this constant could depend on y. Okay? So there might be some additional terms that just depend on y. They cannot depend on x. It would have to be a function of just y. Okay? So, so now that I have that, I can try to figure out what would be that constant. So now take a derivative of this with respect to y. Take the derivative of what I just found with respect to y, and what do I get? When I take a derivative with respect to y, I get x squared y plus, and the derivative of this with respect to y is 0, so plus 0, plus the derivative of this function, the constant y. Okay, so I don't know what that function is, but with respect to y, it's some function. But this has to be equal to x squared y, so I can actually look at what the derivative with respect to y has to be is x squared y, and I do get x squared y plus 0 plus some other junk that I don't want. I want this to be 0 as well, so the constant actually has to be a constant, And as long as this is any constant, it would work. There's not just one potential. If there is one, there's infinitely many potentials that differ by constants. Okay? So it turns out that this function works. You can see that that function that I have here in yellow, the derivative with respect to x of this is this, and the derivative with respect to y of this is this. So yes, it is conservative. That's the f function I wanted. The c of y could be any constant, any number would work.
But like we can say that it's not a function of y.
Exactly. So
that's the only way in which it would work.
right. If it was a function of y with a non-trivial derivative, then this derivative would not be equal to what it needs to be, which is x squared y. So this tells me that whatever this function was of y, the derivative with respect to y is 0. So if I integrate that, I get a number, a constant, with respect to y. It was already a constant with respect to x, now it's a constant with respect to y, so it's a constant. Okay? So what we do is, in general, we do that step of, we take one of the two components that they give me of the vector field, integrate it with respect to the variable, and then take the derivative and compare with the other component. So another trick that you can do is the following. So suppose that this was, if this vector field is a gradient, if they're just asking me, is G conservative? There is one more way to check, which is the following. If this is a vector field, then it has to be the derivative with respect to x, derivative with respect to y. Each of those components has to be a partial of some function f. But remember that if this is conservative, that means that there is a function f that is continuous, differentiable, that has this property. But those functions satisfy Clairaut's theorem, which is that the second mixed derivatives have to be the same. So, if so, then the partial of f with respect to x and then with respect to y has to be the same as the partial with respect to y and then with respect to x. So what I can do is, this is a partial with respect to x, so I can take the derivative with respect to y. This is a partial with respect to y. I can take the derivative with respect to x and compare. If those two match, these are partial derivatives of a function, and then I would know it is actually conservative without actually finding the potential function. So, so take x, y squared plus 3x, which is the first component, and hit it with partial with respect to y, and then you say that we get 2xy. You take the second component and you hit it with respect to x, and what you get 2xy. So these are the same, and this is Clairaut's theorem, and because they coincide, this is going to be a conservative field, so f exists and G is conservative. And you would find it the way I found it in the previous slide, which is by, okay, I know that the first component is a derivative with respect to x, integrate that with respect to x, then take the derivative with respect to y, and compare with the second component. Any questions about this process? Do you want me to do it again? So let me just spell it out again here. That the first step to find f such that the gradient is g, what I did is take the integral of the first component with respect to x. This is going to be a function of x and y plus a constant. So this was a half x squared y squared plus 3/2 of x squared plus a constant that could depend with respect to y, and then you take that whole thing and you take derivatives against partials with respect to y of what you got above, and that is with respect to y, I get also x squared y plus this, and this has to be equal to the second component. So that gives me a hint of what this derivative needs to be, which is 0, and that takes me that this is a constant. So just pick it to be 0, and that tells me that the function that I was looking for was this function. Okay, going back to the previous lecture, remember that we actually proved this. We proved that the vector field, we first derived that the vector field of a gravitational force is given by something like this. And then I calculated that if you take this little function f, the gradient of this function is this one. So that means that gravitational fields are conservative. And that means that if I do line integrals of gravitational fields, those are really easy to integrate, even though they look very scary to integrate in a line. They are saying that these are, if I take a path in space and I have this gravitational field and I want to integrate it along this path, which was the integral that dictated the work, which is a very important quantity to compute, the theorem of the fundamental theorem of line integrals tells me that I just have to evaluate at the end minus the value at the beginning to find the value of that work. So what seemed like a very complicated integral last time is actually very simple, because you just have to evaluate this function at where you start and where you end, or rather where you end and subtract the value where you started of this function. So you can actually compute the work very easily in like very complicated gravitational fields, which is, of course, like this is just very important, that you can do this quite simply. Okay. Let's do another example where I want to compute the this line integral. And remember what this meant. So remember this notation. We compared it to line integrals, and this just says that it's the same as the line integral of the vector field with these as components. So the vector field 2x 2y dot dr. Okay? I can try to do that integral by hand, but if this one was a vector field that is conservative, then I can use the theorem of line integrals, and I don't have to do these integrals that are going to be somewhat complicated to compute. Because I have to, for example, I'm going to have to do the derivative of this vector and do the dot product of this, evaluated at this times the dot product with the derivative of that vector. That's going to be quite messy to do by hand. So is this vector field conservative? Is that a gradient of a function you know? X squared plus y squared does the job. Was that a guess, or did you do some integrals? You guessed. That's a good guess. This is the gradient of x squared plus y squared. I have to, so this is going to tell me this is great. I can use the fundamental theorem of line integrals. I just have to figure out what is the value of this little f at the beginning and at the end of my path. What is the origin? At 0, I'm at 0 minus 1, comma, the square root of 0 plus 1. So I'm at minus 1, 1. And at 3, I'm at 9 minus 1, 8, comma, 3 plus 1, 4, square root 2. What is the value of f at the end? That will be 8 squared plus 2 squared, which is 66. And f of the beginning, 68, thank you. I was so excited with execute order 66, but 68, okay. So that's 68, and f minus 1, 1 is 2. I can do it better when I'm not without a voice. Okay, so we are going to evaluate using the theorem of line integrals, so the fundamental theorem of line integrals, maybe. We can evaluate f at the end, 68, minus the value at the beginning. So the value of this integral, of this line integral of a vector field, is just 66. Let me show you how, if you didn't have that guess of like, okay, yes, this is the potential is x squared plus y squared. If you blanked, how do we figure that out? We would figure it out like we did before. I want to find an f such that this is the partial with respect to x, partial with respect to y. So you take that 2x and you integrate it with respect to x. That is x squared plus a constant. But in this case, because the function was a function of x and y, the constant is a function of y. So now you take that and take a derivative with respect to y. And what do you get? X squared is 0 plus the derivative of y. What is this supposed to be? This is supposed to be the other coordinate of the vector field, so this is supposed to be 2y. So now the derivative of your function, of your constant function, is 2y. So you integrate that with respect to y, and you get that this needs to be y squared plus a constant. Now that constant, let's call it k, it does have to be a number, because now this is not a function of x. It has to be really a number. So what I get is that the constant function has to be y squared plus a constant, and I had that the rest was x squared plus the constant function. So the function f has to be x squared plus y squared plus just any old number. That will work. So you could have picked x squared plus y squared, that's it, or x squared plus y squared plus 1. You usually pick the easiest one you can find.
Or is that,
Oh, I see what you mean. No, it doesn't always work. It turns out that it doesn't always work because what I have here, for example, it could have been that this had an x. Suppose this was x plus a function in y gives me 2y. There's no way that this constant, this function here, could cancel out that x. Okay? So for it to work, you do have to have that the crossed second partial derivatives, they equal each other. If they equal each other, what you're saying will always work.
okay.
But if you don't have that property, then it will not work. And here you cannot find any function that satisfies that property because this function would also have to have some term in x, but this function was supposed to be constant in x. So it can't be that it has an x in it. Yep, good question. Okay, so some more theory. The line integrals of a vector field are called path independent if for any two paths we actually get the same value. So if you look at what had just happened with conservative paths, with conservative vector fields, the fundamental theorem of line integrals tells you that it actually did not matter. The path did not matter at all. It was just like where you started and where you ended, right? So the fundamental theorem tells me that if f is conservative, if I take a path, this is going to be, it is conservative, so it's the gradient of some function, and it is just going to be f of the endpoint minus f of the beginning. So as long as I start and end in the same path, I could go in two different ways. I could, if I have to go from here to here, I could go this way, or I could go this way. It doesn't matter to the fundamental theorem as long as you go in a continuous way. In a continuous differential way, then it doesn't matter. So when that happens, if you have vector fields that are path independent, that the integral, the line integrals does not depend on what path you take to get from one point A to a point B, and we call them path independent. And then you can see that we have already found a bunch, which are precisely those that are conservative. You could have path independence without conservativity, but we know that this g is the gradient of a half x squared y squared plus 3/2 of x squared, for example. So it's conservative, so it is path independent. Okay? So it turns out that for those integrals, the path to get from A to B is irrelevant. You will always get the same answer. That's interesting. So yeah, we also say that a parametrized curve is a closed curve or a loop if it starts and ends at the same point. But if you have an independent, so if you have a path independent vector field, then you will always have that the line integral is 0 for closed paths. For example, if you consider a conservative field, the line integral tells me that will be, the theorem of line integrals tells me that the answer will be f of the beginning minus f of the end. But if if the end and the beginning is the same thing, then it's f minus f equals 0. Okay? So, so for example, if f is a gradient, then and C is a loop, f the r will be the integral over C of this, and it will be f of the end minus f of the start, which has to be 0 because they end and start at the same place when you have a loop. This is an example. This is an example of a loop. This loop is just going around a circle. It's going from 0 to 2 pi. So it starts and ends at the point 1, 0. So it is a loop. It's a closed curve. So let's try to figure out what is this integral. The integral of this vector field, where C is an ellipse. So this ellipse looks, they're telling me that the path is an entire ellipse. So it's going to be something like this. And I can parameterize it starting from here. Maybe that's the wrong color. I start here, I go, and end at the same place. So that is going to be a closed loop. So if I'm able to show that this vector field is conservative, then I am done. So I need to try to figure out a potential function for this field. So how do we do that? How do I check? Well, I could, for one thing, I can do the cross partial derivatives to see if they coincide. That would tell me that this is conservative, so I can move ahead. Or I can actually find the potential. So let me try to find the potential. Since I have to do an integral, I would rather do an integral of this one with respect to y than of this one with respect to x. I hope you agree. So we're going to integrate this one with respect to y and see what happens. So if I integrate this one with respect to y, what do I get? X e to the xy. Is that right? So if you do a u substitution or something, you can see, let's just check that the derivative of this with respect to y would be this. So that works. Plus a constant. But that constant now is a constant with respect to x. Okay? So now I have to take the derivative of this with respect to x and see what I get. Okay? So let's see if I take the derivative with respect to x. X exy plus this possible function with respect to x. Now, the first one I have to do a product rule. So this is going to be e to the xy plus, and then the derivative is going to be x squared e to the xy plus whatever the derivative is of this function with respect to x. And that has to be equal to the first coordinate of my vector field. This has to be equal to 1 plus x, y. What did I do? I don't think I did this right. With respect to x, take the derivative of this with respect to x, a y comes down. So this is x, y, e to the xy. So these two things have to be equal, but this one, by the way, this one being the first coordinate of my vector field, but this one, if I expand it, it is e to the xy plus xy e to the xy, which is what I have here. So if I set this to 0, then I win. So just pick c prime of x to be 0, and pick the constant function also to be 0, and I can take f to be, where is it? To be this function. x e to the x y. That function has the property that its gradient is the vector field that they gave me. Okay? But that means that that vector field is conservative. And that means that if I integrate on a closed loop, I get 0. So let me go back here. This, which is the same as this, where f is x e to the xy, has to be 0 because C is a closed loop. Okay, so from here to here, we prove that f is conservative, and from here to here, we are using the fact that the path we're doing is a closed loop, so the theorem of line integrals would tell me that it's, like m minus m equals 0. So I'm just looking for one function that works. So if you tell me, if I reach this conclusion, then I just need to find one function here
Gotcha.
such that this whole thing works as a potential.
Okay, and just so that kind of like satisfies the equality regardless of
Yeah.
what the...
As long as you find one that works, then it is a conservative vector field, and then we can apply our theorems on conservative vector fields.
Thank you.
You just have to find one that works.